Hello, folks. I'm Kalyan, and I'm working as a tech lead at Oracle. I'm here to talk about the most critical challenges in modern platform engineering. So, how to execute a massive infrastructure migration without dropping a single customer request. So, the goal isn't just to replace the old system and do with the new system. The goal is to design for the zero downtime. Any enterprise, any high throughput SaaS environments, this is not just a nice to have feature. This is commercially imperative. So we are going to talk about I'm going to talk about a case study. So on how we successfully migrated a critical legacy gateway to a modern, highly available architecture. The transformation was executed without a single service interruption. So this case study has proven that a complex infrastructure migration can be possible with zero downtime. So let's start by defining why we have zero tolerance for downtime. So when you process billions of requests and using a platform, and if you want to replace the platform with a new platform, like you need to copy all the functionality of the old system onto the new system without any disruption. So the risks involved with that is people usually use the testing on the old system, and like people write the synthetic tests like unit tests and integration test on the old system, and they replay it on the new system. And once the tests pass, they simply cut the traffic from the old system to the new system. So that solution doesn't work if we have if you have a lot of undocumented changes in the old system and there is a lot of tribal knowledge in that went in there. So what's the solution here? So we realized that automated reliability engineering and continuous validation using actual production traffic like will work. Like these are the methods to prevent service interruption. So this led us to a strategy of a phased rollout combined with advanced shadow traffic validation framework that we need to that we use to test the production traffic safely. And yeah, so let's look at the system that we have to replace. So the system that we are trying to replace is a legacy monolithic gateway based out of Ruby and Sinatra. So it has a session management and authentication and authorization logic, and also routing all together jammed in one service in one monolith. So those associated with this monolith is the blast radius. One change in routing will could if a if there is an issue with routing changes that could severely impact other concerns on the same service. And there were also resource concerns like the Ruby and Sinatra. It's an open source and it wasn't an advanced gateway, so it is not leveraging the multi-core compute resources that we've been using. And also, if at all we need to scale a single concern, we have to scale this uniformly. So there is a scalability issue as well. And there was also the operational risk was also mounting. There was less expertise in the company with the Ruby, and also there were a lot of security vulnerabilities. And yeah, and these are the reasons why we want to replace this legacy model with a modern architecture. So the tight couple root architecture was the root cause of our scalability issues and the operational risk. The tight coupling of concerns meant that, like I said earlier, that a minor update to routing could break the authentication stack and vice versa. And there was also a scalability inefficiency as well. And this is draining the compute resources. If at all we need to scale a concern at the peak traffic, we have to scale this uniformly. So our objective was clear: transition to a modern enterprise gateway and decouple the concerns while maintaining the continuous service availability. So by we need to migrate this complex service safely without any downtime. So this is where the real challenge began. So migration, like what are the migration challenges and validations that what are the challenges and what are the validations that I'm going to talk about them here. Undocumented legacy behavior, like moving away from the legacy bot to the new gateway. There was a lot of undocumented changes in the legacy gateway where traditional testing cannot catch if we run the test cases on the new system. And then most dangerously, and earlier I mentioned we gotta use a shadow replay mechanism to run the parity. There, the performance impact was there could be performance impact with that. So if this shadow, I'll deep dive into this shadow traffic framework in the later slides. So there was a performance issue. I'm going to talk about like how did we overcome that performance issue. So the performance impact is one, and another one is, well, like we need to came up with a workaround to skip the double execution of the request. And other one is we want to offload the authentication logic to a different independent microservice. So these were the challenges with the migration. So let's dive into how the validation, the shadow framework will work. This is the core technical innovation that actually enabled the downtime, zero downtime, with a state marking shadow framework. So we had to solve the double execution problem as well. So our solution was based on replay mechanism that works in 5 steps. There was a processor on the legacy gateway, and that processor, whenever the legacy gateway receives a request, it usually processes the request. And by forwarding the response back to the client, this gateway will actually asynchronously use a processor to run the parity. So this processor will actually copy the customer request and fire it on the new con gateway system. And before firing that, it will create a parity ID, and it also saves the downstream response and also the client downstream request and also the client response, both of them in a NoSQL store. And it fires the same request with the added query parameter called parity ID, and it replays on the new system. So when Kong receives it, Kong should do the same thing as the legacy gateways does, and it should forward to the downstream. So to avoid, if the REST API call is read, then there is no issue. But if it is other than read, we want to skip the double execution. For that reason, we deployed a interceptor on the backend system. So whenever backend receives this request, the interceptor will kick in, and whenever interceptor sees the parity ID, it basically retrieves the like downstream response from the cache, and it responds to the Kong gateway, and Kong gateway forwarded back to the legacy gateway. And when everything is in place, the all of this the processor will run the parity and save the differences in a NoSQL store back. So now let's look at it. I'm going to talk about what are these differences and all of that in the later slides. So now let's look at how we implemented this framework across in the migration. Okay. So the migration it's an 8-phase implementation work. The first one is planning and provisioning. I used a Terraform, and all of the routes in the old gateway have been coded in the YAML format for the Kong, and all the infrastructure changes, everything I use Terraform to document for the deployment. And that's where the planning and provisioning went in. And once we have it ready, there were benchmark test results from Kong. So we used them, and I did some of the load testing, and then we deployed Kong as a separate cluster. And then the next step is shadow framework, like the validation part. So here the validation part, while validating in the validation, basically we cannot validate entire production traffic, because if we validate entire production traffic, the traffic will double, and we also have to scale the backend or downstream systems to handle all of the traffic. So for that reason, we sampled the one fifth of the traffic gets replayed on the new Kong gateway, so that if we run this over the period, based on the probability, the assumption is that all of the API routes and all of the functions will be covered. So that's the idea here. And the next step would be authentication offloading. So the plan is, this one is a bigger topic. So I had taken the similar approach to offload this authentication and authorization. Let's say, like, to simplify that, the next step is offload the authentication concern has been offloaded to a new microservice. And then testing. Like I said earlier, we use the sampling and we played the month the traffic. And after that, if this has been like once there are no differences, we had incrementally rolled out the traffic from old gateway to the new gateway, and then we did the final cutover and then retired the old gateway. So that's the eight phase implementation framework that we followed for this migration. So let's look at now how the shadow traffic, like what has the shadow traffic validation has revealed. Okay, which I've clipped. So the shadow traffic findings were most critical. So because they're gonna reveal the hidden production behaviors, and whatever the synthetic test has completely might miss. So we performed two key verification. First, we looked at downstream system verification, downstream request verification, comparing the request payload Kong sent to the backend against the legacy system, the legacy gateway sent to the backend. And another one is client response validation, like what the legacy gateway has been forwarding to the clients for the same request, and also how what Kong is sending back to the clients. And the next one is progressive sampling. Like I said, the plan was to not run on the entire traffic, rather to sample the traffic, like one fifth of the. We use a random function to divide the request ID, and based on that, like we implemented a sampler to sample the traffic, and so that the processor will not replay the request for every production request isn't replayed on the new system. So using this, so these results were used for the before the final to make any corrections in the new gateway and before cutting over the real traffic to the new gateway. Let's look at the operational impact and benefits. So the ultimate measure of success for this project is that we achieved zero customer facing incident despite processing millions of requests. This wasn't just about downtime, it delivered tangible business benefits. We saw a cost reduction, 20% cost reductions in the compute resources because using the modern architecture. Furthermore, we deployed a vendor supported platform that the vendor supports the security vulnerabilities patches. And there were a lot of out of the box features that comes from the vendor supported gateway. And also like we were able to, and the vendor gateways, it's compliant with security. So we don't have to do additional work when it comes to the security. So it is compliant. And there were side effects like automated deployments, and crucially, the new architecture has reduced the mean time to recovery, and there were automated rollbacks, making the system more reliable. So let's talk about that new architecture and fundamental changes like we can build and scale. So let's dive into that 20% cost efficiency because it is a direct result of moving away from monolithic architecture. The biggest driver was independent scaling. We no longer had to scale the entire heavy Ruby stack just to handle the lightweight authentication checks. By decoupling the authentication workload, we optimized the resource allocation dramatically. And secondly, we eliminated the Ruby bottleneck, like not being able to use the multi-core. And we got more work out of less hardware. And finally, we saw a massive reduction in operational overhead and vendor supported patches and automated deployment pipelines. So the efficiency gain was just one time save, wasn't just one time saving. It is continuous benefit that funded the that will be funding the future innovation as well. Let's look at the broader architecture benefits this transformation has unlocked. So the architecture shift is foundation. Now the authentication auth concern can independently scale, and there were multi-tenant capabilities, and also we don't have to do a migration if the company brought in an acquisition or so. Like it has multi-tenant capabilities. For suppose in the use case the company acquired a bunch of other companies, so we were able to use the same platform to route the traffic to their backend services once the companies merge. And regarding compliance, also the it is simplified because of the vendor support, and also we were able to use the latest libraries. Even if the vendor doesn't support, we were able to apply patches if there were any security vulnerabilities. And there was engineering velocity as well, because we don't have to, because we minimize the blast radius and the number of unit tests that we run when we deploy a change to a gateway, when we deployed authentication. The mean time has substantially dropped. So this has improved the velocity of the engineering team as well. So let's see, like, how did we execute it without it dropping a single request? Let's see in the next slide. So, and what are the key success factors? Definitely, the shadow traffic validation is the key factor for the success. And another one is incremental rollout, just to reduce the blast radius if something goes wrong. And the infrastructure as a code, the Terraform, using Terraform has speeded up the planning and provisioning of the new gateway easily. And then automated analysis, like in the traffic validation part, we were automatically able to evaluate the differences between the old and the new gateway and able to quickly fix the functional issues in the new gateway. And then yeah, phased implementation. This phased implementation also helped us maintaining the production stability and the throughput and the transition, like we basically reducing the blast radius as well here. Here we're going to talk about the lessons learned. The success factor we just covered aren't just API gateways. They form a universal reference or a blueprint for any complex monolith to microservice transition. The big key takeaway is that for legacy system, the validation over testing is superior. It definitely helped us. The synthetic test, all of this would have helped, but definitely would have given the confidence that we got from the validation. And we have also learned about the store and the forward pattern is crucial for the risk management. And it also decouples execution from the actual backend state, ensuring that like the shadow traffic doesn't execute one request twice. And finally, the validation results also helped us to fix the problems in the new gateway. So yeah, these lessons are applicable whether you are like these lessons will help not just with the, like I said, the authentication and authorization concern was separated from the legacy gateway using the same pattern. So this is not just for gateways. This can be applicable when you're trying to migrate any backend infrastructure, any backend REST API kind of infrastructure. So this can be applicable there as well. And what does this mean for the future? So in conclusion, this case study validates the complex infrastructure transformations can be executed while strictly enforcing the service level objectives. We proved that phased rollout and the traffic validation enables a truly seamless migration. The business impact was substantial. We achieved zero downtime, delivered over 20% in infrastructure cost reductions, and significantly enhanced our security posture. This project provided comprehensive methodologies for industry, demonstrating like how to execute high-stake migrations without service disruptions. Yeah, the core key takeaway is invest in automated reliability engineering and the validation framework for these kind of migration patterns, or to modernize any backend infrastructure that relates to this pattern. Okay. Yeah. Thank you. Now I'm open for any questions, and also just in case if you don't agree or if you see any improvements, just find me on LinkedIn and connect with me. We can chat over there. Thank you. Thank you. Thank you for having me.